Okay, thank you. Um, well, I've been asked to give an account of my personal perspectives on the early history of string theory and its development out of dual resonance models, and to talk in particular about matters I was involved in and how it seemed how these developments seem to me. So from that point of view, it's a distinctly personal perspective. And I'll mention in particular the people that I worked with. Um, I'll mainly concentrate on the early years of development um, as Paolo De Vecchio and Adam Schwimmer put it, in the 4 years from 1968 to 1972, the complete theory, bosonic theory, was constructed consistent with Lorentz invariance and unitarity, requiring a space-time dimension of 26, though some of the space dimension could be compactified to be very small, but with the deficiencies of a tachyon and no fermions. But along that time, through the work of André Neveu and John Schwartz and Pierre Ramond, fermions and fermionic degrees of freedom were incorporated into the theory, producing a chiral theory in 10 space-time dimensions, free of tachyons, and offering the prospect of a unified theory of the fundamental forces on the Planck scale rather than the original objective of a theory of the strong interactions on the nuclear scale. Again, as De Vecchio and Schwimmer put it, these developments, especially those up to 1972, occurred within the conceptual framework of S-matrix theory rather than from the quantization of the dynamics of some continuous system, such as a rubber band or elastic string. Any such system is equivalent to an infinite collection of harmonic oscillators, and it can provide a metaphor for the space of states of the dual model that we're talking about, but that is limited to the kinematics, the statement about the space of states. That metaphor can't be extended to the dynamics of the system because the energy levels of the vibrating string or fixed length or harmonic oscillator are evenly spaced, where it is the squared masses of the energy, that is, the energy squared of the dual model that are evenly spaced. So the string model that was proposed by Nambu and Goto in 1970 and 71 did provide a system whose quantum theory yielded precisely the dynamics of the dual model, as well as the kinematics, and included its interactions. So over the last decade or so, a number of informative accounts of how string theory emerged from the Veneziano model or dual resonance model have appeared. And in 2012, a large collection of first-hand accounts appeared in the Birth of String Theory book, edited by Capelli and others. But it's necessary for us all to bear in mind how friable recollections can be 4 or 5 decades later. Memory is often selective, with each author reconstructing the past in his or her own way. And of course, prescience benefits enormously from hindsight. Using present terminology and conceptual frameworks to describe past discoveries can distort unintentionally the nature of what was understood, when and by whom. In writing histories, it's essential to reconstruct the conceptual framework of the past. Here's a few articles that I've written in this area. Now, in this talk, I'll try and cover a number of developments that I saw at first hand or nearly first hand, up perhaps to the 1980s if I get there, although I'm doubtful about that, and concentrating on the earlier years, as I said. So I should begin with the context of S-matrix theory, the conceptual framework within which these early developments in practice occurred, and talk about the early attempts to interpret dual resonance models in terms of physical pictures. Then I'll discuss the proof of the absence of ghost states which would have given rise to meaningless negative probabilities and the broader significance of the mathematical structure underlying that elimination mechanism. And this leads on to the quantization of the string proposed by Nambu and Goto. And I also at the end hope to say a little bit about monopoles and lattices and algebras. So I began as a research student in Cambridge in October 1967, working for a PhD in theoretical elementary particle physics under the supervision of John Polkinghorne. At the time, along with Berkeley, Cambridge was one of the two main centers in the world for S-matrix theory. The previous year, 1966, within weeks of one another, two books had appeared. One by Eden, Lansoff, and Polkinghorne, and another by Geoffrey Chew. Superficially, at least in their titles, the books only differ by a hyphen. But philosophically, they differed more radically, in that Chew was much more of a fundamentalist, a charismatic evangelist. In a waspish review, Abdus Salam began by noting that the art of writing monographs with an unashamedly personal bias appears to be lost. But there are a few practitioners of the art still around, and among these is Geoffrey Chew. And Salam went on to comment, one may disagree profoundly with Chew's views, but one cannot but admire the complete suspension of disbelief with which he can approach his view of the physical reality. Central to Chew's philosophy was his bootstrap hypothesis. That is the proposition that the requirements of analyticity, which were supposed to be related to causality, and of unitarity, which was fundamental to the probabilistic interpretation of the theory, perhaps together with some suitable asymptotic assumptions that energy, such as Reggie behavior, should determine uniquely the scattering amplitudes, i.e. the S matrix. Along with this went Chew's principle of nuclear democracy, that no particle was more fundamental than any other, but rather that all are in some sense bound states of one another. Chew's view grew out of the work of Stanley Mandelstam in large part, which was less than a decade earlier. Analyticity in energy had been studied for many years, but Mandelstam showed how to study scattering amplitudes as analytic functions of a number of complex variables, which he took to be the squares of sums of momenta. And this language, Mandelstam variables, immediately became part of the universal language for studying scattering amplitudes. Chew recruited Mandelstam to Berkeley, and Chew's preaching was based on Mandelstam's writings. It was said at the time, Mandelstam was God and Chew was his prophet. But in this case, God was actually an agnostic. Mandelstam himself needed firmer footing for his work than a hypothetical bootstrap, and he was never completely convinced of Chew's philosophy. For him, at that time, that basis had to be perturbative quantum field theory. So ELOP, the Eden, Lansoff, Olive and Polkinghorne's book, is much more didactic and analytical. Its 4 chapters, each primarily written by one of the 4 authors, cover successively first background, secondly analytic properties of Feynman diagrams, that's perturbative quantum field theory, and thirdly high energy behavior of quantum field theory, perturbative quantum field theory. So here, perturbative quantum field theory is regarded not so much as a potentially realistic theory of strong interactions, but rather a theoretical laboratory for studying the analytic and asymptotic properties that the S matrix might possess. It provides a solution of the unitarity constraints as a formal power series. The fourth chapter, written by David Olive mainly, develops S-matrix theory. There he shows how unitarity implies that the S-matrix must have the same singularity structure in the physical region. So here we remind you of the Mandelstam variables. I've drawn there the center of mass frame with an incoming three-dimensional momentum P and an outgoing momentum P prime scattering through an angle theta. And Mandelstam said that these should be studied as functions of S and T continued in the complex plane. And I'm using here a Euclidean metric, which is the spatial parts minus the time parts for reasons that are convenient later. So this is the variable S and the variable T of which we study the behavior. So the fourth chapter of Eden et al.'s book is full of equations like this, bubble equations, which Olive developed to describe unitarity equations. So the S matrix is written as a delta function part of the particles not scattering at all, plus a connected part in which they do scatter. And then its Hermitian conjugate is written in this way, so there's a factor of I involved, and this leads to the equation at the bottom as encapsulating unitarity in 2-to-2 scattering. But of course, when you get to higher energies, there are more particles that can occur, and so you have to include intermediate states with more than 2 particles in the equations. And then you can, in fact, deduce from the unitarity equations, this is what Olive does in that chapter, that the, say, 3-to-3 scattering must contain a pole corresponding to an exchange of the particle here in suitable circumstances. And in this way, by studying unitarity equations, one can infer in effect that the S matrix has to have at least all of the singularities that occur in perturbation theory. So it's noteworthy that of these 2 books, and it's rather remarkable that Elop is still in print nearly 60 years later. So in his book, A Brief History of String Theory, a historian of science, Dean Rickles, suggests that the string model was not an immediate success because there was an S-matrix motivated reaction against the string model. Because if there's just one single system underlying all of the different resonances, then that implies a fundamentality that is an anathema to most physicists working on the dual resonance model. That is, in my experience, I'm fairly confident, completely untrue. While many of those, if not most of those working on dual models in the period from 68 to 74, had either worked on S-matrix theory at some point or spent formative years in S-matrix theory centers such as Berkeley or Cambridge. Almost without exception, they were not rigidly committed to choose principle of nuclear democracy as an exclusive ideology any more than Stanley Mandelstam was. Rather, they regarded the dual model as potentially providing a set of amplitudes that perturbatively satisfies the postulates of S-matrix theory in a way that quantum field theory in its perturbation theory does. But the dual model is conceptually different, and it's an alternative theoretical laboratory, an alternative power series solution to the unitarity equations, but one in which the individual terms have Reggie asymptotic behavior. I actually wrote to Rickles and asked him why he said what he said, and he said that he thought that must be the case, but he hadn't had time to talk to people about it. So the immediate issue that led to Veneziano's proposal of a quite simple expression for the relativistic scattering amplitude, as he put it, was the phenomenological issue of how to combine resonance contributions to models, that is, summing writing the low energy behavior of the scattering amplitude as a sum of contributions from a number of resonances, with Reggie contributions at high energy. What did you do in the middle? Did you just add the two effects together, which seemed likely to end up with some sort of double counting? So alternatively, you could take the view that the resonances and the Reggie contributions might provide alternative or dual descriptions of the scattering amplitude. And the term duality in this context originally refers to this possible duality between resonances and Reggie poles. Well, so for many, duality seemed to make more sense than the interference that you would get if you added the two terms together. But there were people who argued that it was mathematically impossible to have an amplitude that could be written either as a sum of resonances or as an asymptotic expansion in terms of Reggie contributions. And the large part of the initial motivation of Veneziano's paper was to show that wasn't impossible by giving an example of a simple function. Now, within 6 months of that original suggestion of Veneziano, his suggestion for 2-to-2 scattering 4-point function had been generalized to n-point function describing the scattering of arbitrary numbers of particles. So this is his quite simple expression, as he put it, a ratio of gamma functions, beta function, and it has the poles at integral points along a trajectory alpha of s and along the parallel lines, which are called daughters of that trajectory, and it also has an asymptotic, Reggie asymptotic behavior. But one thing to note is that if the intercept of the trajectory here is positive, then the basic particle of the theory will be a tachyon, that is a particle that moves faster than the speed of light. So in early 1969, Zirakoba and Holger Beck-Nielsen introduced an elegant representation of the endpoint function, which was very influential in both understanding its mathematical structure and eventually in its physical interpretation. So this expression wrote it as an integral over n variables, z, an expression which was invariant under Möbius transformations in Z, and therefore one had to factor out a variant measure, Möbius invariant measure of the Möbius group in order to get a finite answer. So in the summer of 1969, things were moving fairly fast that time. Both Nambu, in a contribution to a conference in Wayne State University, and Fubini, Gordon, and Veneziano, and also Susskind, showed that the endpoint function could be factorized in terms of the space of states of an infinite number of harmonic oscillators. That is, the endpoint function could be written as the sum of a product of smaller amplitudes summed over the poles. So that was in June 1969, and in doing that, this is Nambu's notation. He introduced a field which satisfied the wave equation, and so had the Lagrangian. It was a field with d components, where d was the number of dimensions space-time, and it lived in a two-dimensional space. So altogether, at this point, the number of dimensions you've got is d space-time dimensions, which are recurring in some sense like internal dimensions, living on a two-dimensional space. So d plus two-dimensional system altogether. And the solution to the wave equation, of course, it enables you to write it in terms of harmonic oscillator creation and annihilation operators. And from that, you can write down what the you can write down this expression for the energy. So Nambu suggested that the internal energy of a meson is analogous to that of a quantized string of finite length, or a cavity resonator for that matter, as he puts it, whose displacements are described by the field phi. But the energy of the dual resonance meson in Veneziano's model is not that. It is the square root of that. So what you have here is a system moving in a 2 plus d dimensional space with coordinates both sigma and tau space-time coordinates, and the normal space-time coordinates occurring as internal dimensions, and stretched over some finite length in sigma space, with tau rather than phi 0 being the time variable for the system, but a problem over interpreting the energy, which was not focused on. So this enabled you to factorize this representation enabled you to factorize the expression for the endpoint function. And in terms of the space created by the harmonic oscillator annihilation creation operators, in terms of an elegant expression in terms of vertex operators V, which we'll see have very magical properties, which have widespread applications, not only in this context, but also in mathematics. So another approach to this, which does actually give you a calculational framework for calculating the amplitudes. In the case of Nambu and others' attempts, there wasn't a relationship really between the calculation of the amplitudes, which you could do with the harmonic oscillators, and the theory underlying it. Another approach where there was an actual analog model, so it formed an analogy in the sense you could reason with it rather than just a metaphor, was given by David Fairley and Olga Nielsen. And it was first described in an unpublished reprint of Olga Nielsen called An Almost Physical Interpretation of the Integrand of the Endpoint Veneziano Model. And then in more detail in a joint published paper between Nielsen and Fairley. So Nielsen's preprint, which is undated, he has been described by him as having been poorly circulated, as was an earlier version of the paper, which was written in 1969, and that version no longer seems to exist. And the preprint has three sections. In the first, Nielsen states the proposition that the integrand of the endpoint function is in the form that he and Kober had obtained, is the exponential, the extremal value of a certain integral taken over a disk. And he remarks that David Fairley has told him that this extremal value is given by the heat generated in the conducting disk by steady current distribution. And Fairley also suggested an elegant proof of this. So this analog model was discussed at greater length in a published paper by Fairley and Nielsen, where they show that also that the loop integrand, people had already constructed loop contributions within a sort of mimicking the procedures of quantum field theory, that this can be obtained by replacing the disk by an annulus. And so in that way, they had an analog way of calculating these contributions. So, and later this was shown to work for the endpoint amplitudes. So Fairley came to the analog model by searching for an interpretation of Kober and Nielsen's expression. But Nielsen's approach was different. He said it's possible to interpret the generalized Veneziano amplitude as a model in which the mesons are thread-like structures. Hadronic interactions are conceived of then as processes in which threads join at the ends, points into longer threads, which then split into shorter threads. So I think that's the first description of the way that we now think of interactions happening in string theory. So Nielsen defined a map from the disk of the analog model into physical three-dimensional space, defining a surface that can be regarded as what he called a time track of a thread, or more accurately, a system of threads. This would seem to be this first description of this. And as the threads, as they move through space-time, they trace out a time track. Nielsen also gives an alternative way to understand mesons as threads by regarding the Veneziano model as an approximation to the contribution of a very complicated Feynman diagrams. So he assumed there was an underlying theory, this is typical of his sort, which was in which it was the very complicated diagrams you could draw, which, because of the strength of the coupling constant, dominated the expression for the amplitude. And he had to argue that these very complicated diagrams were, in some sense, effectively two-dimensional. They defined a two-dimensional surface. So his approach was really fundamentally different in that he thought it could derive the Veneziano model as some sort of approximation using complex random structures from an underlying field theory. The time track that was described by Nielsen was called a world sheet by Susskind in a paper written at the end of 1969, in which the internal structure of mesons are described by the degrees of freedom of four-dimensional rubber band with a quark pair embedded in it using the harmonic oscillator formalism. Susskind argues that this model reproduces the generalized Veneziano model, and he observes that the level spacing separating rotation excitations of hadrons is very nearly the universal quantity of order 1g of E squared. And only systems known from quantum mechanics to possess this property are harmonic oscillator systems. But as we've seen, there is a problem with that because this is not the energies that are being identified. So a number of authors in that collection of essays, The Birth of String Theory book, comment on the fact that over this period, up to the beginning of the 1970s, the term string theory was not really in common use as such, at least not as a single term. It only came into common use after the paper, Nambu's subsequent work, which we'll and Goto's work, which we'll discuss. So Monton commented the string theory term only came into common use in 1972. And Veneziano wrote, the identification remained qualitative for some time until Nambu and Goto first formulated in a precise way the classical action of a relativistic string, and then its quantization established the connection between the spectrum of the dual resonance model and that of the quantized string. So over this quite short period from Veneziano's paper in 1968 until the end of the 1970s, developments we're now going to get on to of the Nambu-Goto string, we'll get on to soon, there was a really fast activity. So by the summer of 1970, 2 years after Veneziano's original paper, the interpretation of the dual model as a material string or rubber band involved the dimension of space-time plus two dimensions with two space-time coordinates, a state space that was too large, really, and discrepancies between the energy of the dual model and the energy of the material string, and the possibility that those states might render the model inconsistent. In fact, these deficiencies were all actually deeply interrelated, and they sort of cancelled out in the correct way of thinking about it, as I try to describe. Well, I started working on these matters, or beginning to think about them, in my last term in Cambridge in the summer of 1970, when David Olive, who was lecturing in the AMTP in Cambridge at that time, returned from leave at CERN and gave a course of lectures on dual models in May 1970, based in part on the work he'd been doing with Daniele Amati and others at CERN. He presented it with his characteristic simplicity and elegance and depth, and the subject strongly interested me, having worked on S-matrix theory, because the sense he conveyed of an emerging, elegant mathematical structure, and because it provided an alternative theoretical laboratory for studying the properties of the S-matrix. So when I arrived at CERN myself as a postdoc in September 1970, I found an air of excitement surrounding these ideas, and a number of physicists, mainly young ones, working on them, inspired in large part by the leadership of the staff member Daniele Amati, whom I mentioned. Over the coming 2 years, I was there as a postdoc, nearly everybody making fundamental contributions to dual models, or dual theory, as it sometimes was pretentiously called, passed through, gave seminars, or came to stay. And in 1971, David Olive returned as a staff member. More than one person has drawn attention in describing this to the words of William Wordsworth. Bliss was it in that dawn to be alive, but to be young was very heaven. Actually, Wordsworth was writing about the French Revolution. It didn't turn out completely harmoniously. But these are lines from his poem, The Prelude, about his development. And they go on, actually, I think that they go on in the immediate lines, nearly immediately afterwards, apposite as well. When reason seemed the most to assert her rights, when most intent on making of herself a prime enchantress to assist the work which then was going forward in her name. By which I mean that what struck one was that the model had a mind of its own. You might try to force it to be a theory of strong interactions or to do various things, but there was a degree of rigidity or purposefulness about its structure, and it had its own reason. So initially, I worked on trying to renormalize the dual one loop amplitudes by some analytic process. And here, if you take a loop in which the string has two ends, and so that's evident in the mathematical expressions we have, and so that means that particles in some sense can join from either side, and if they join from more than one side, you get a diagram in which if you take the momenta here, which I've colored, and you take their sum to be space-like and sufficiently space-like, then the expression actually converges. But if you want to, for example, consider an amplitude in which there are no particles on the inside, you want to try to continue that to zero. But as you try to continue, you come to a singularity, and that singularity causes a divergence. But if that singularity were a pole, then you could continue round, or even if it were a cut, you can continue round. The problem is if it's a cut, then the expression you get once you've continued round to get to the place where the internal momenta is zero, you end up on top of a cut and so get a complex answer. So I was trying to play around with that idea, and come back to and when I was doing that, Marty told me about work that Lovelace had done. Claude Lovelace had been studying the same sort of diagram, and what he was trying to do was not the approach that I was trying to adopt there, but he was trying to change the parameters of the theory so that cut, which actually violates unitarity, because the cut means that if there is a cut there, in some sense in this channel here, what you have is something propagated which is not described by pole. And within the framework of S-matrix theory, all of these things should be poles, or if they're cuts, they should describe the transfer of more than one particle. But what was happening here in this contribution was that you had a cut which was violating unitarity. And so Lovelace sought to make it a pole. And he found that he could fiddle with the integrand by varying the dimension of space-time and by varying the number of states that were removed by some mechanism of Ward identities or whatever. And what he found was that he needed 26-dimensional theory, and he needed two infinite sets of identities. So, but then when that singularity does become a pole, it didn't really help what I was trying to do, because you would end up on when you put the masses to zero, you would end up on a pole at the origin, which actually in the end corresponds to the graviton. But the second thing I ended up trying to do with Richard Brouwer was, as like many other people, was to try to generalize what Veneziano had written down, which Vissar had already generalized to a sort of function that's written down here, which instead of having the sort of one-dimensional integral you originally had with Veneziano, you had a two-dimensional integral. And in fact, in the end, he's describing closed strings. But we managed to use a space which had n dimensions. But then we realized that if you had such a space, there will be little chance of eliminating the negative norm states. The point I wanted to make by making this illusion was just, apart from showing you the sort of things that people were thinking about, is to is to emphasize that as you tried anything, you came up against the same sort of problems. So when the dual model was first factorized using these oscillators and that, it was immediately evident that you had the potentiality for negative norm states. The time components, just as with electromagnetism, the time components would tend to create ghost states that in the sense of negative norm states. In electromagnetism, there's Ward identities which remove these. That's one way of thinking about it anyway. But the problem in the case of the dual model seemed to be much more severe because in some sense there was an infinity of them, one for each oscillator mode. But Miguel Virasoro observed that if the intercept was of the trajectory was 1, then what that meant was that you had a tachyon. It meant that you also had a massless spin 1 particle, but you also had an infinite set of conditions, which eventually De Vecchio and Del Giudice wrote in this form here. So you could write down a set of conditions, which an infinite in number, which would clearly at least eliminate some of the ghosts. The question was, would they eliminate all of them? And to that end, you would want to consider the algebra of these operators. So this algebra here is called the Virasoro algebra. There's a slight irony about that because Virasoro didn't actually write it down in his paper. He wrote down the operators and he explained in this enormously far-sighted way that you had these conditions on the physical states. But because he only considered the conditions with positive n, he didn't write down the full algebra. He wrote down the algebra without this C number term there. So the full algebra has a C number term there. And that was eventually, actually people wrote a number of papers like following Virasoro without putting that term in. And eventually Joe Weiss, who sadly died about 8 or 9 years later, he observed that there had to be this term there, which is not difficult once you appreciate that that it has to be there to see that that is an absolute necessity. So the physical states satisfy these conditions, and what you find is that it may be that there are a lot of not just that it just doesn't. It's not just that it eliminates states, but when you get to this dimension of 26, you find that you actually create lots of null states. So now the reason you would find that is if you, and this was started by Brouwer and Charles Thorne, you start looking at the physical states of the system, and you can find quite quickly that if they decided to allow the dimension of space-time d to vary, which was not much done at the time, and they found that if the dimension of space-time exceeded 26, then actually there were ghost states in the theory. So it was not a trivial matter to establish that the theory had no ghost states. But if d was less than 26, they didn't immediately find any. In fact, there aren't any there. And at this borderline of d equals 26, the state makes a transition from having from this is the wrong way around, I think, from being negative to being positive. I should have a minus sign. As d is 20 bigger than 26, this should be negative. It's minus sign. So something remarkable happened at d equals 26, but it wasn't initially appreciated exactly how remarkable that was. So to study back in the end of 1970, to study the whether these states, negative states, were there or not, Brouwer and Thorne studied the space that was at right angles to the physical space. So the Virasoro operators applied to some state will create states which will be orthogonal to all physical states. And so if you can work out what the norms, what the signature of that space is, you can, by taking the complement, work out whether the states, whether the physical states have any negative norm states in them. And so that's the problem that they started. And they wrote a seminal paper in which they remarkably introduced a number of concepts already known to the mathematicians, concept of verbal modules and contravariant form and so on. And so the problem comes down to calculating the matrix of states that look like this, which you can do just using the algebra. So it's a function of C and H. Now, in a parallel development a bit later, which they didn't know about, Victor Katz produced a remarkable formula for the determinant of this matrix, which can be used to solve many problems connected with this. But at the time, Brouwer and Thorne studied this matrix and established that for a long way they couldn't find any dose, at least if the dimension was less than or equal to 26. But another approach was taken by Dal Giudice, Di Vecchio, and Fubini. Rather than try to study the states that were eliminated in the way that Brouwer and Thorne were, they tried to create all of the physical states. And they did this by introducing creation operators which would commute with the Virasoro generators and therefore map one physical state into another. And there was a physical motivation, if you like, for these operators because they described the coupling of the massless spin-1 particle, photon-like particle in the theory. And doing that, they were able to construct d-2 dimensions of these physical states, which were not in themselves superficially enough to give you all the physical states. And so these physical states that you made with these DDF operators were, because they satisfied nice annihilation and creation operators, those physical states were necessarily nice and positive. But the physical state equations here might have other solutions because you haven't got all the solutions to the equation. To get all the solutions to the equations, you really need d-2 dimensions of these, d-1 dimensions of these things, not d-2. But in fact, what turns out is that when the dimension is 26, these are essentially all the states because every other state is null. So just lots of null states come in when the dimension is 26. So with Richard Brouwer, I tried to start constructing the states that were missing. In other words, to find another set of operators which will create physical states. Now, the ones that DDF had written down were the ones associated with the polarizations of the d-2 polarizations of this light-like, of this spin-1, massless spin-1 particle, like the photon states, but in d dimensions, the d-2 components. And if you look at the longitudinal components, then they automatically vanish, so you don't get anything from that. This integral trivially vanishes. But you can try then to look at the other dimension. You can take in another like vector, which has a non-zero inner product with the momentum of the particle, the like momentum, and try to see what that does. Now that you would not expect to commute with the Virasoro algebra, because it's nothing to do with the physical state really, not immediately. But what you might hope is that you get some nice algebra, and indeed you do get some nice algebra. If you take the commutator of this this sort of longitudinal state operator with the Virasoro operators, you get something which has a very nice expression in terms of the vertex operator, comparatively nice expression. And so what you want to do is to somehow use this algebra to modify this in order to get something which does commute with L, with the Virasoro algebra. So what you need to do is to seek some additional part to add on to this longitudinal operator to make something which commutes with the Virasoro algebra. And then you will have d-1 sets of operators which commute with this, which in principle look as though, you've still got to prove the details, but look as though they will create exactly the right number of states. And Richard Brauer found the solution to this issue. Again, there's a fairly elegant expression. In the end, it becomes a commutative problem, and it's not too difficult to solve once you think about it the right way. And so from that, you get a modified operator which does commute with the Virasoro operators. And although that, when you look in dimension 26, that is creating more states, but those states actually, when you subtract off a bit of what you've got already, are all null. So you find that the difference between the new operator you've introduced and an operator, essentially a Virasoro-like operator made from the existing transverse modes, that you get a set of operators which generate all the physical states, but this part of them generate null states. And so what turns out to be the case is that in 26 dimensions, the dual model behaves like the photon, like in electrodynamics, so that it's not just that it's not just that there are less states, but there are you lose 2 dimensions of states. And so remarkably, in 26 dimensions, it's as though you have 24 dimensions of oscillators creating the physical states. So while that was going on, with Charles Flawn, I was trying to find another way of solving the problem, which was to characterize the DDF states, which you can do by posing, in addition to the Virasoro conditions, the condition that K times the AN oscillator gives you 0 on the state. So this is a sort of light-like component of the annihilation and creation operators. And together, this gives you an algebra. And once you realize, which it took some time to realize when it all came together, that in fact, as I just said, that there are really only 24 dimensions of oscillators there, then you can by suitably clever manipulations prove that the physical states consist of a DDF state plus a null state, and this is in a form in which you aren't this form of the theorem, the no-ghost theorem, which has previously been proved there by Brauer. This form of the no-ghost theorem doesn't involve writing down the creation operators, and that the DDF operators, and although that means that you don't have quite the same physical picture, it does mean that it's a more transportable mathematical statement, and it's a statement which actually has had some importance in mathematics because it was a crucial ingredient of Richard Borchard's proof of the Coleman-Norton conjectures about the relating to the monster group. So some fairly we might regard as rather esoteric part of mathematics. That proof relies on the no-ghost theorem, and is a proof of which that work is work for which Borchard's got the Fields Medal. So in that sense, you can see that it's a fairly deep structure that's emerged in the dual model. So along with this, contemporary with this, if you like, the appropriate action was first written down for the dual model, and the correct string interpretation was given by Nambu in the summer of 1970. So Nambu was actually going to speak at a conference in Copenhagen. And on his way to the conference, something inauspicious happened. The conference was in August 1970. He was driving from Chicago to California, which is not the direct route, of course, but he was dropping off his family for a holiday before flying to Europe. And his car broke down in Death Valley, and he was delayed by 3 days, missing his flight. And effectively, he decided he'd missed the conference. So he abandoned going to the symposium, but he assumed that his notes that he prepared for the talk might be useful, and he'd actually sent those to Copenhagen in advance. And he thought that they would be published in the proceedings. In the event, copies of the notes were circulated to those at the meeting, but not more widely. And although some limited knowledge spread by word of mouth, these notes did not become generally available for many years until they were published in Nambu's selected scientific papers in 1995, where they're described as undelivered and unpublished. In his contribution to the Birth of String Theory book, Nambu comments, "I think I must thank the goodwill of fellow physicists who kindly attached my name to the area action, even though few people may have seen the notes." And I think that's certainly true. The notes were not available at CERN when I was there, as a postdoc in 72. So some months later, in May 1971, Goto in Japan independently proposed the action, in part influenced by earlier work of Takabayashi. And this led to the action being called the Nambu-Goto action. So there's only a small part of the paper which actually mentions this, is this part here. It's mentioned very much en passant and almost dismissively. So this is the part that I showed you on the previous slide, the part of his undelivered talk, in which he actually writes down the action. If you decode the symbolism, the action's written down there. But what he says, you'll note in the comment at the bottom here, is that it's obvious that equation 24, its action, leads to nonlinear equations. More complicated equations involving curvature would not be only nonlinear, but also have higher derivatives. And that's the only comment he makes about solving it. At that point, he almost dismisses it because it gives nonlinear equations. So I've written it, this is how we tend to write it today. and what it describes is a surface X of sigma and tau, and it is the Lorentz invariant area of that surface, and that's the action. And the idea is to minimize that. To give it the dimensions of action, you need t, a constant t over c, the speed of light, and the dimension t has the dimensions of tension. You can think of it sort of as the rest tension of the string. When Geoffrey Goldstone wrote this out, he was amused. He amused himself by calculating what that tension would have to be for the particles that came out of the theory to have masses of the order of the mass of the nucleon. And the answer was 13 tons. He thought it was rather amusing. You get a macroscopic number like 13 tons in there. But of course, if you want this theory to describe not nuclear physics, as we now tend not to use it directly, but to describe events on the Planck scale, then that tension has to be 10 to the 40 times higher. So this action principle is intrinsically geometrical. The expression here is reparameterization invariant, and you can write down the equations of motion for this, and as Nambu says, superficially they're nonlinear. But if you impose a condition to say that the coordinates you're using are orthonormal, that is these equations here, then they suddenly, all of the nonlinearity collapses out of them. And this is exactly like the principle you would get if you just take a particle moving along a geodesic, and the geodesic condition will also look nonlinear unless you require that you use a parameter which is normalized to have be uniform along the string, along the path of the particle. So if you impose those conditions, what you get out of it is the wave equation. And once you have that, then you can quantize this system. So there are two ways of thinking about the quantization. One is as a canonical approach, in which you say you'll select your coordinate tau to be proportional to x in some direction. And here, the convenient thing to do is to take a light direction. And then once you've done that, you can solve for two of the components of A, essentially. But you have to, because you've made a non-Lorentz invariant choice for the coordinates, you have to describe how you would implement Lorentz transformations to show that different choices will give equivalent theories. And so for that, you introduce the generators of the obvious choice of the generators of the Lorentz algebra. And you need, given these conditions here, for those algebra to close in the appropriate way to give you the algebra of the Lorentz group. And that actually only happens if the dimension of space-time is 26 and the intercept of the regular trajectory, if you like them, is 1, so you have a massless particle. So what you get out of this is it reproduces exactly the results that you found in the dual model. Now, there's another approach in which you forget about you quantize covariantly, but then you impose the Virasoro conditions as physical state conditions. And then you find that the absence of ghosts then, of course, requires the dimension be 26 and the intercept be 1. Or you can have the dimension being less than 26 and the the intercept being less than or equal to 1. But then you get longitudinal modes present. That is, you get modes present in the quantum theory, which are not present in the classical theory. They disappear in the classical limit. So with these developments, the connection between Nambu and Goto's model of the string, which is, so to say, a different physical system from the one that didn't work earlier, but that once that was established, then the string picture had a firm basis, and the idea of the dual model being string theory became more clearly established. And you can see that from this graph here. What this graph is a histogram of the number of papers which had the word string in the title dealing with the dual model. In other words, before 1973, although there are papers which mention elastic strings and so on, other strings, they aren't in the title. I just took this as a simple way of indicating the prevalence of the way people were talking about it. From Nambu's work onwards, the term became much more prevalent until in 1976, interest in string theory as a whole starts to wane. So here's Nambu and Goto's paper. It wanes. There's a little bump when Polyakov gives his reformulation of string theory in the 1980s. And then the whole takes off in 1984 when Green and Schwartz proved the anomaly cancellation. Should I stop at this point?
No, there's still plenty of time.
Okay, I'll go on a little bit. Feel free to disappear. Just before I left CERN after 2 years there, there was a seminar on the work we'd done, which I just described briefly, on quantizing the relativistic string. And this was in the meeting that we'd had every Thursday at 2 p.m. for all the time I'd been there. It was a meeting which was very relaxed. People were very open, almost always very open about their ideas and what they were dealing with, thinking about. In contrast to atmospheres I've experienced elsewhere at times. And I think it was partly that the whole subject was disapproved of by nearly all senior physicists. They thought that this was a complete waste of time and self-indulgence and so on. And so there was extra frisson of enjoyment about it because it was somehow forbidden. But there were exceptions to that. I've seen most notably Daniele Amate and David Olive. But in that seminar, as people who actually were working at CERN, there were many visitors who came by, but there were people working there included Lars Brink, Edward Corrigan, Paolo De Vecchia, Paul Frampton, David Olive, of course, and Claudio Rebbe, Joel Shirk, and Charles Thorne. So that group would meet sitting around the wall in a small room for Thursday afternoons. But when somehow this seminar was advertised, I mean, they were all advertised and anybody could turn up, but basically it was only those working on the subject who bothered to turn up in general. Except in this case, the whole place was completely flooded. It may have been that word of what had happened in terms of quantizing the string spread. It may have been that Gell-Mann, who was in CERN for a while, had asked for a private audience about it. But anyway, there was a much larger audience and it had to relocate to the main theory conference room. So the 2 years that I spent in CERN really built up to that sort of crescendo. And I have to say that in terms of my scientific work, nothing was quite as exciting again. The pleasure of collaborating with Thorne and Rebbe and Goldstone was quite exceptional. Then I went from CERN to Durham, where Ed Corrigan also came, and we worked together on fermion theories. At that time, that is 1972, Neveu and Schwartz and Ramond had produced a fermion theory, which was more challenging in some ways when constructing fermion scattering, in particular in the methods that we had at our disposal at that time. But it looked as though it was all going to be consistent, but the problem was to actually construct things like the scattering of fermions with fermions, and that indeed was what we worked on at that time. You had to, in the case of the fermion scattering, make sure that there weren't any spurious, that is, non-physical states being exchanged between the fermions, and that resulted in having to put in a correction factor, which is shown here, a certain determinant. And at the time, we initially didn't know how to calculate the determinant. John Schwartz and one of his students, I think, numerically calculated that it was something like 1 minus x to the quarter. And then they found that it seemed to be exactly that. And after that, we and various other people proved it. And what you found after that was that with certain subtleties about parity, which were significant and related really to the fact that you should be thinking of this as a chiral theory describing particles with parity violation, that with those provisos, the thing was beautifully dual. So along at this time as well, Mandelstam was showing that the Nambu's Lagrangian applied with suitable end conditions of describing a surface going between two, say, incoming strings and two outgoing strings, so that Lagrangian actually described the interactions and not just the spectrum of the theory. So everything was contained in Nambu-Goto's action. But in another part of the theoretical physics world, there were great developments in understanding gauge theories and in the understanding asymptotic freedom. And the result of this, and the result that actually, at that point, with the methods then available, work in dual theory produced very elegant results, but it was technically a bit demanding. It resulted in, over that period of from 1973 onwards, of the subject as we saw in the graph I showed you, attracting less attention. And on December 21st, I think it was 1973, David Ollie wrote to me from CERN, where I was in Durham. He said, very few people are now interested in dual theories here in CERN. Marty and Fubini independently made statements to the effect that dual theory is now the most exciting theory that they've seen, but it's too difficult for them to work with. The main excitement is the renormalization group and asymptotic freedom, which are indeed very, very interesting. So I stayed in Durham for 2 years, and then I spent a term at the Institute for Advanced Study. And when I came back, I went to Cambridge as a faculty member and spent summers often in CERN. And there I would work with David Olive. And the first thing that he was working on, and I joined him, was trying to understand the work of the 't Hooft and Polyakov on monopoles. So the 't Hooft and Polyakov had shown that there are classical solutions to gauge theories with Higgs mechanisms, which have classical solutions which have non-zero magnetic charge. And the magnetic charge that you find in that case obeys Dirac's quantization condition for magnetic electric charges. So in the 1930s, Dirac showed that you could have isolated magnetic poles in a theory with electric charges, but that if there was to be a proper quantum theory, then there would have to be a relationship between the electric charge and the magnetic charge. There was a quantization condition. And so this was a really breathtaking development at the time, about 1931. And so if you have a radial magnetic field, then it describes a net magnetic charge inside it if it has this form. And what Dirac showed was that for this to have a consistent quantum theory, you had to have that Q, any electric charge times any magnetic charge divided by h bar was essentially 2 pi times an integer. And so what the monopoles that the 't Hooft and Polyakov found satisfy these conditions, so potentially could exist in a quantum theory, although they were classical objects. And what people have started doing, particularly David, was to generalize this into other gauge groups. And there you have not just one electric charge, but a number of charges for the possible electric-like charges of fundamental particles in the theory will be connected with the weights of the representations of the gauge group. And there are corresponding possible magnetic charges for classical solutions to these theories with Higgs mechanisms. And they obey, of course, a generalization of this condition, which various people established and which we studied. And this condition now means, here the Dirac condition meant that if you had any charge Q, then electric charge Q, then G would have to be an integral multiple of some constant times 1 over Q. And so it immediately told you, if you have this condition, that both electric charge and magnetic charge had to be quantized. That was part of the fascination for Dirac. And so the analog of that quantization in this general context, where you have a group that is bigger than the U1 group of electromagnetism, is that you have Q and G sitting on lattices. This is sitting in the lattice of weights of the group, and G is in some dual lattice to that. So in suitable units, if you have a gauge group G, Q sits in the weight lattice of the group, and G sits in actually the weight lattice of another group. And it's non-trivial that there should be another group. It's a group which has roots which are essentially the inverses of the roots of the original group. So associated with each group G, there is, if you like, a dual group, which is not necessarily the same. At least the global structure will be different. So if you start with a gauge group SU2, its dual group is SO3. It's the same algebra, but different global structure. If you take SO2n plus 1, where n is bigger than 1, then it's actually a different group that you get a symplectic group. And duality is a reciprocal relation, so they go backwards and forwards. If you take E8, which doesn't have a center, doesn't have a non-trivial global structure, then you get E8 back again. So E8 is self-dual. So there's a lot to study about these monopoles and the properties they have to do with their weights, and I'm not going to give a talk about that here, but I know that what I noted just for this purpose of this little discussion was that this led us into studying lattices and learning about lattices and learning about the duality between lattices and in particular the particular structure of self-dual lattices. So David, with his then student Klaus Monschen, conjectured that not only did these magnetic charges satisfy the condition you need if they were particles in a quantum theory with appropriate electric charges, but they would at the quantum level there would be a theory with the appropriate gauge group, and these theories will be dual to one another. So, in other words, if you start with a theory in which you have microscopic electric charges, but you have classical solutions which are extended objects which have magnetic charge, there is a dual description of this theory in which the roles are interchanged. And that was Monton and Olive's conjecture, which was enormously far-sighted and a precursor of many of the ideas about duality, which are now very prevalent in elementary particle physics, or fundamental physics, I should say. So this led us on to start thinking about what happens if you consider vertex operators associated with these lattices. So if you take, if we have too many dimensions in string theory, and so you compactify some of them into very small dimensions. But the way you do that, there are various ways of doing that. If you just have a circle, there's really just cut it round. But if you have many dimensions, then it forms a torus, and the torus is found by taking space modulo displacements by some lattice, and then the momenta are associated. The possible momenta are quantized and associated with the dual lattice. And what one found then, if one looked at that, and now I'm just going to be very vague, is that the operators of string theory naturally gave you operators which produced the group you were looking at. And so what this showed you was that loosely speaking, compactifying the extra dimensions to on a torus which was dual to say a root lattice of some or weight lattice of some group would then enable you to write down in the theory operators which would satisfy the algebra of the group. And so it would mean that the symmetry was present. And we particularly focused on the idea when we studied this was in 1983 when we were then in Charlottesville on leave. It seemed particularly interesting to look at the cases in which you had self-duality, and that led you, if you require, you need lattice to be even, that is the square lengths of the points on it to be even integers, and if it's then self-dual, then you're led to a very limited number of possibilities in Euclidean space, which say in the dimension has to be a multiple of 8, and in dimension 8 there's just one C8. In dimension 16 there's E8 cross E8 and a version of SO32, and in dimension 24 there are actually 24 of them, so there's more possibilities there. But 16 in particular led to these, and this actually foreshadowed the construction of the heterotic string. So I guess the point I'm trying to illustrate in all this is that there's a whole sequence of ideas, and these ideas connected in many ways with a lot of deep mathematics, all coming out of these simple initial suggestions. And I'm going to stop there.
Thank you. Does anyone have any questions they would like to ask? If not, I'll go ahead. I was wondering if you could say something about your views on the dual resonance model period in terms of your conceptual understanding. Did you think that the dimensionality was like a pathology? Did you think that theory would be ultimately correct? Because you did leave the field around 1976 to work in monopoles and instantons and so on and so forth. So I was kind of wondering about your kind of choice to do that. Did you not think the theory was correct? Was it for financial reasons? And how did you view the theory conceptually in terms of its correctness?
Right. So I think certainly the attitude, the prevalent attitude in 1970-ish and so on was that you should look around for the right model. Once you realized about then that certainly 70 to 72 that there was a preferred dimension of space-time, which had been 26 for the bosonic string and was 10 for the Neveu-Schwarz-Ramond string, that maybe then in the right dimension, this would come down to be 4. And in any case, you could curl up the dimensions and so on. The developments with the methods that we had at the time, which could be improved on as they were in the 80s, they were still interesting, but they weren't the most easy way of calculating everything. That those, as I said, it was technically quite formidable, and that was not so much a deterrent for me, since I'd sort of grown up with it, but it was a deterrent for I put it like this, that I was conscious of the fact that it's going to be difficult for my graduate students to get jobs because the interest had gone away from it, and it was a difficult subject in that sense. And so it is actually the case that my immediate decision, these things are used as rationalizations to some extent, but I was conscious of the fact that my students, my first student in Cambridge, Roger Horsley, worked on this for some time, eventually moved into phenomenology, and ended up at Edinburgh. But my second student was Nick Manton, and he started working on matters like this, but his interest, well, as soon as I started telling him what I'd learned about monopoles, his interest shifted there. And I was rather conscious of the fact that given my teaching and other duties, I couldn't do research on a subject that was different from what my graduate students were working on. I couldn't be helpful to them if I were working on something else because I just didn't have the time to do two things with a fairly substantial teaching obligation. But I never thought we were leaving it forever and then one would come back. I didn't know that, in fact, more or less everything we did ended up being connected with it, however much you wanted to get away from it. So I certainly, and certainly then in the later 70s, when we started talking to mathematicians, Graham Siegel, who was then in Oxford, and then subsequently Katz and Frankel and so on, in fact, the work that we started doing in Charlottesville was in part motivated by the fact that mathematicians were very interested in it. And we were interested in what the mathematicians were doing, and indeed started being interested in trying to understand the monster group and the way of representing that, because it seemed interesting and seemed connected in ways that I couldn't quite put one finger on. But as I tried to indicate, there was this sort of inner reason about the model that one could follow. But the answer to your question is that firstly, that we weren't being very purposeful in trying to force it to be something, but rather following it. That's what at least some of us had learned. And secondly, it was motivated by consideration by the fact that it was not such a suitable subject at that time for research students to go into.
I see. Thank you for answering my question. I just wanted to say if you could say a little bit more about the connection. So could like the kind of work that you were doing, is that something that led to the cosec construction, like the later work with monopoles? Or was it a bit of a break, like kind of jumping into a different subject?
Well, yeah. So one of the so one of the theories that one studied around that time was the studied the way that theories defined taking their values on groups were equivalent to fermionic theories. So the prototype of this, in some sense, was the Sine-Gordon and Turing model that were equivalent. And then, so this was a question of different ways of representing systems that were equivalent to one another. So it related to these ideas of duality. This was an idea of duality, two different ways with different classical limits of formulating a quantum field theory. And a very prescient paper was, a very seminal paper was written by Edward Witten at the beginning of the 1980s, in which, called non-abelian bosonization, in which he looked for conditions under which so-called Westermino-Witten model of a theory where a field, two-dimensional field is taking values from the group manifold is equivalent to free fermion theories. And he wrote in this paper, he set up something, but he didn't discuss didn't discuss explicitly whether the energy momentum tensors for the two theories were the same. And so David said, well, he's missed this bit out. He doesn't miss things out unintentionally, presumably he hadn't worked it out. And so it can be proved that the energy momentum theory tensors for the two theories are the same, so that they really are the same theory. They've got the same content. You could probably then know, you could then know the dynamics were the same, as we saw in a much more blatant case with the string earlier. It's not much good unless you can say that the energies are the same, the dynamics is the same. Well, it can be good, but not everything. And so we were in Aspen in 1984, and so we sat down and started trying to prove the two things were the same, and we found they weren't. We found there was a difference between them. Now, the previous year in 1983 had been with David to a meeting in Berkeley, one of the first meetings at what became MSRI, which then was then down on campus. And at that, Dan Friedan talked about the Veneziano algebra and about conformal field theory, which we knew obviously by now was related to all of this, and in particular about the representations of the Veneziano algebra. And so when we started calculating, sitting in the sun in Aspen, the difference between these two energy momentum tensors, we found that they had central charges which were on the list that Friedan had given us. And nobody knew. So what Friedan and Hugh and Schenker had done was to prove that the representations of the Veneziano algebra, which were unitary, had to sit on a certain list of an infinite list of possibilities with an accumulation point at one. And only one of the points, I think the first one, half, was known at that time. And when we started calculating, we didn't know whether these things had been interested, but we found that they were starting to fill in all of these gaps. And so we actually, that way, managed to prove that some of these representations were unitary and construct them. And then when we got back to Cambridge, and I got back to Cambridge and we worked with Adrian Kent, who was my student, we found the Cosec construction. So we had a version of the Cosec construction, but it wasn't sufficient to prove everything when we were in Aspen. Does that answer the question?
Yeah, thank you very much.
So there is a lesson from this at that time, which my general lesson I gave to my students was find a paper written, read it carefully and see if there's any little gap that he's left. As a way of finding things interesting.
Are there any other questions?
Excuse me, Professor Goddard, Thank you for this amazing and insightful talk. I also had a question about dualities and fundamentality, particularly like the history of the concept and its evolution in physics community. For instance, like Montan-Olivet's duality and the Lagrange dual group. Uh, could you please share some of your thoughts on like fundamentality and duality and how perception of these concepts evolved over time in physics community and how your own perception of them evolved?
I'm
Thank you.
sorry, I'm afraid my hearing isn't very good. Could you please just repeat at least part of the
Oh,
question?
sorry.
Yes, to see.
My question was about Montan-Olive as duality and Langland's dual group, and also some
Yes.
of your thoughts about like how your perception and how general physics community perception of more perhaps philosophical questions of duality and fundamentality evolved over time.
Ah, well, I'm not sure that I can do that very well, certainly not without preparation. But um, when um, when we found this dual group, we're working with John Noyce in 76 or so, when we were working in Summer and Sun. Soon afterwards, maybe the next year, next Easter or something, I went to a conference in Nottingham on mathematical education, because I was interested in mathematical education, relationship between education in the schools, particularly in England, and the university course. And at that, playing a prominent role in that conference was Michael Atiyah. And so one evening after dinner, he was saying he was interested in the relationship between of Skirm's work, essentially, and the relationship between the Sine-Gordon model. And so I started telling him, well, there are also these monopole systems, which at that point he hadn't heard about, and that there was this funny group that came in, a sort of dual group. And he immediately said to me, that is Langland's dual group, and started telling me a bit about how it came up in Langland's theory. And that was, I think, in 1977, and it was another 30 years or so before Whitman and Seiberg explained this in more detail. So at that point, he gave very remarkably quick, of course, but it was a tear explanation. But the understanding of it took a long time, and I'm not sure I can say anything useful about it now without stumbling. Sorry.
Thank you very much.
If there aren't any other questions, we'll end the talk here. Yep, Professor Goddard, thank you very much.
Thank you.